Hi everybody, today we're going to continue the deep dive analysis of the Hermes Ransomware. In the last two videos we unpacked the payload and then we did a quick overview of the general capabilities. I did a kind of table of contents overview to get an idea of where the indicators of compromise functions are, and so we can get a general context of what's around those IOC locations. So in this video we're going to focus all on the cryptography. So again, once this video series is complete, I'm going to upload the marked up database into my GitHub page so you can download it to kind of analyze at your own time and you can compare the results you get. But we don't really need an introduction for this video, so we'll just kind of get into it. So if we go back to our kind of IOC information to discover that we talked about in the last video. So for the cryptography, we want to determine the crypto algorithm and what type of key it has. And then we want to figure out how the crypto key is conveyed, how it's stored, basically the process of surrounding the crypto, really looking to see if we can discover any vulnerabilities in the protocol so that we don't have to pay the ransom if we have our files encrypted. So let's go back to the database. And I don't remember exactly what the function was called that did the crypto, but we want to start there. So I'm going to go to the flat view, and I had the functions windows open. And this is why I sort all my stuff alphabetically. And I'm just looking at the functions. I see crypto encrypt file. So that's the function we want to look at because that's going to have the encryption function. So let's go back to the graph view. And so we're just going to scroll through this and we're not going to focus on every detail. We're really looking for the cryptography IOCs. So we're going to get a general idea how it works, but we're not going to be concerned with the exact implementation details. So you can see we check the file attributes and then we open an existing file. Once that's open, we get the file size. And then we see some comparisons here to a large number with some logic. And then we come over here so you can see the crypt generate key. So this part up a little above where we compared to a large number, it's very possible that could be something where you're encrypted in chunks. Maybe you have different options for fast encryption versus full encryption, where you encrypt maybe the first X number of bytes. There's different ways that you can implement the crypto functions. And that part we're really not concerned about because it's not all that important. What we are concerned about with how this key gets generated. So if we look at the crypt generate key, this is done out of the WinCrypt API, so it's a Microsoft API. So that means we know it's going to be implemented correctly. It's not going to have any big vulnerabilities where they custom coded. So let's look up the MSDN for crypt generate key, and we can see that our second parameter is the algorithm ID. That's going to tell us what type of key we're generating. So let's go back to the Ghidra. And so we 66610, in fact, sorry, we need to see what the options are for this. So for the algorithm ID, I opened this up already opened it up. And so I'm going to just do a search on 6610. And we see that it's calculating AES 256 key. And we can see all these start with CALCG. So let's go ahead and go back into Ghidra. And we're going to right click the constant, set equate. And we're going to look for the constant to replace it. So do CALG, and we notice nothing's coming up. If we go back to the flat view into this data type manager, I'm going to search for the CALG here. And then, so you see here, we don't even have an option for AES. So I'm not really sure why that is, that it's missing out of this Ghidra header files. But the fact that it is, I could either create my own structure and add it in there, which is a little bit more work than is really worth doing it just for this one or two crypto functions. So I'm just going to put a semicolon for comment. I'm going to put AES 256 here. So this is generating the AES key, and the generated key is going to come in the last argument, which is this local 8 here. So I'll hit L to label. I'm going to call this the file AES key. So we generate our key. And then we do some math stuff. We allocate some space. And then we set file pointer. With set file pointer, the fourth argument, so 1, 2, 3, 4, is where you're setting file pointer to. We set ed equate here. And this is going to be file begin. And you can look those up in MSDN. I'm just more familiar with the constants, so those I tend to remember. So we set our file pointer back to the beginning. And then we come in through and read the file. The second argument for read file is the buffer, and we can see this EBX. If we scroll up, this is probably, we see right up here where we allocated space for. So we basically allocated space to read the file into. So we read it in, and then we encrypt a file. So you notice this should be the space where we write it in is EBX, and that's not anywhere inside in this crypt encrypt. If we scroll down just a little bit further, we see crypt encrypt with EBX here. So you may be wondering, why do you call crypt encrypt twice? And then why do you have the EBX only in the second API call? And that's because with some of the Microsoft APIs, particularly where you need to know a buffer size, you can call it once with null arguments. You see here ECX is null, and we pass null for a lot of these. And when you call it with all null arguments, you're going to get the size needed in the size buffer. That's local 24. In this case, so now we're encrypting it where we know the size, and it's encrypted in the buffer EBX. We're encrypting with the file AES key, so this is the AES 256 key we just generated. So we know we're encrypting each file with an AES 256 key, and we know it's a new randomly generated key for each file because that generate key was done inside this encrypt file function. And since we already labeled this function that it's encrypting a single file, we know this, so I call it on every individual file. So we encrypt the file, and then we set a file pointer back to the beginning. See here, we'll set the 0, right click. We can do set equate or hit the E for the shortcut key, and see this file begin again. And now that the file is beginning, you see our EBX here was the buffer we just encrypted. We write the file back to the beginning. So we basically encrypt it, and then overwrite the file with the encrypted buffer. Now we scroll through a little bit more, and we see here a big constant again, but this looks like it's in kind of the ASCII string range. So let me go ahead, right click that, and do convert. And I see this is, it looks like the Herm, and then right click, convert. And so we see this is the Hermes string in little endian. So it's local 10, I'll hit auto label. I'm going to call this Hermes string. And we keep scrolling through. We copy that Hermes string in this local 60, hit auto label, call this Hermes string copy. Now we set our file pointer, and this one's EX. So the 2 here, I'll hit ed equate. This one's going to be the file end. And they'll double click that to change it. And now we're converting something, an integer, to an ASCII. We concatenate what looks like a pipe onto EAX, which is, let's see if we can see, which is our Hermes string copy. And then concatenate something else onto it. And then we have the pipe. So we're basically building out a string. So this Hermes string is some type of string that starts with the Hermes identifier, and then has some other variables in here. Instead of tracking down exactly what these are statically, it's going to be easier if we want to find out what those are just to look at it dynamically in debugger. So for the deep dive process, we generally do a mixture of static analysis to figure out what we're doing, and the details we'll look at in the debugger because it'll oftentimes be quicker. So we basically build out that Hermes string, and now we see the second argument is the Hermes string copy that we just built, and we're writing out to the file. And remember, if we scroll up a little bit, we set the file pointer to the end. So we basically encrypt the file with the AES 256 key, randomly generated per file, and then we append this Hermes string onto the end of the file. Once we do that, we're now going to export a key. And so when we export a key, we're exporting the AES key. We're going to protect that exported key with this param3 key. And that basically means you can either export it in the clear where it's readable, or you can export it in a protected manner where you encrypt it during export. In this case, this param3 is encryption function, or key that's going to encrypt it. And that key is going to be exported into this last argument. So it's local 44, I'll hit auto label, and I call this file AES key exported. And so now we need to know what param3 is, so we can determine how that file is protected, or how that key is protected. Well, that's kind of where you see the summary view, satellite view. We're about halfway through the function. Let's continue down and see what the rest of the function does. All right, so looks like I made a mistake here. So this export key, so just from context, I can see here, I thought this was going to be exported key, but it looks like because we're passing it on to, so we called it twice in a row again. So that means I know the shared parameter in between this first call and the second call will be the buffer size. So I'm going to hit auto label, I'll cancel that out, or sorry, copy that, and then this variable, I'm just going to hit delete to delete it. In fact, sorry, let me hit Control Z to undo it, undo the naming. Because that's the size, the parameter before it will be the buffer, In this case, EDI will probably be nulls. That's why it's repeated. And then we see here, we're going to get our local 1C4, and that's going to be the parameter where we output the key. And we can go double check that. Let's check the export key and make sure the first, second, third, fourth, fifth argument is the output key. So it looks that way from context, but we can be sure. So for export key, and 1, 2, 3, 4, the fifth argument is indeed the data, and then it ends with data length. So that means this local 1C4, I'm going to hit auto label, and then I'll paste that name in there, the file AES key exported. So we export a key, and then we write file, which will write onto the end of the file, so append that export a key protected by param3. If I keep on scrolling through, I see I set my file pointer to the end again, and I'm going to hit ed_quate. I see this is the file end. And now I'm just going to scroll through some more. So I see I'm writing some more stuff to the file. In this case, it's local 98. I'm not sure what that is, but let me scroll through a little bit more. I see a large value that looks more like a hex value. And then I see again another file, large number multiplied by set file pointer. So this is starting to look more like an implementation method. So it looks like I've already encrypted the file, wrote it out, you basically encrypted in place. I appended that Hermes string probably as a identifier, and then followed by the encryption key protected by param3. Now I have some more write files. Set file pointer to the end, read file, set file pointer, and then crypt destroy key, set file pointer. So this is really starting to look like potentially code to, because I'm reading, writing, setting file pointers, that maybe I'm having code to either encrypt it in blocks, section at a time, or maybe if something interrupted the encryption to kind of pick it back up again. And so that part looks more like implementation methods, and that's I'm not really concerned about. So I'm just going to scroll through and see if there's anything else that makes sense. So I see this read file, and now I see I'm comparing some byte to this local 48, 45, 52. So that looks like more like ASCII string characters. So let me go ahead and right click this, and I see this is, let's see, where's convert? And I see this is an H, right click, and convert E, right click, and convert R. So this is looking, it's going to be checking for that Hermes string, right click, convert M, right click, convert E, and then I suspect this would be S. Right click, convert S. If those all match, we're going to come down to here, and let's check where this blue link goes towards. Alright, so this blue, we're going to follow it. And then we see we basically exit out if we find that Hermes string. So that kind of gives us more confidence that that previous read writes, all that type of stuff, was some type of implementation in the encryption method, because we're checking to see if we find the Hermes string, which we know is appended right after we encrypt the file. If we find that Hermes string, we exit out. So all those read writes before that is probably just of if we got interrupted in the encryption process, so you can probably pick up where we left off, or it's encrypting blocks, something of those nature. Again, those are details that aren't really interested. From context, it looks like we're encrypting this just once. And we can see when we read this file, it's local 88, which is this FFFFF7 Charlie. And if we select that and scroll over here, we see it's highlighted here. And we see this is basically, the buffer EBP plus this hex plus EAX. And we see we have 7 Charlie, and then 7 Delta, 7 Echo, 7F. And you see how those are all incremented by 1, but the EAX is staying the same. This is basically a way of looping through a buffer. So this is, unfortunately, Ghidra get this wrong maybe 10-20% of the time, where this F7 Charlie really is the local 88 reference, stack reference, but Ghidra didn't pick that up for some reason. So we can fix that by right-clicking, going to, let's say, find it. Let me scroll this up, I didn't see it in the menu. So right-click, there should be references. Alright, so some reason I'm missing this. Let me go ahead and refresh the screen, this graph view, and let's see if this shows up in the right-click menu. And I'm just going to go to the side view and kind of click down to where I was at. And let's see if this works better now. Alright, so this is kind of funny. It has the references, but it's somewhere under the screen, and it's not showing up here. Let me see if I scroll up. Yeah, some reason it won't show up. So the shortcut key is I just hit R, and this will apply references. I hit the plus button, and then I hit the stack, and I put this minus 0x88, hit add, and then we can see if we select the 88, it's that same 7 Charlie here. I don't know why the right-click menu didn't update. Again, the stuff in the graph view, not the kind of best, sometimes it has mistakes. In fact, just out of curiosity, if we select that, let's go back to the listing view and see if it works in here. So we can select this, right-click, and we see here references, and then add edit. So again, the shortcut key R. Again, that's just a good thing to know at Ghidra. If things don't work in the graph view, usually they work in the other views, it's just that graph view really is a little bit buggy. But either way, that's local 88, so this would be local 89, 90, and so forth, but I'm not going to worry about that. So just the fact, but we see the local 88 is what we're reading from the file, the buffer. So that means we're reading the buffer from the file, looking for that Hermes string. If we find it, we exit out. So that's really telling us all we need to know, that the rest of the code is just the implementation details, and we're not concerned about that. So now all we need to know is what that param3 is, so we can determine how we're encrypting the file AES key. Let's go to the very top in the satellite view, and I will follow the cross-references. So I select the function, Control-Shift-F, and we have run cross-reference. I go to third parameter, so 1, 2, 3. In this case, it's parameter 4. So from the satellite view, I'll go back to the top and follow the cross-references, Control-Shift-F. And I see I have a couple of references, so I select the first one. And we want the param 4, so 1, 2, 3, 4. So this global variable is basically the AES protection key. So I'm going to hit auto label and call this, I'll put G for global, I'll put the file AES protection key. And then we'll follow these cross-references to see where this gets set from. Control-Shift-F. And we'll go to the first cross-reference. And we can see that's just where it's getting used inside the function. So if we're looking at these other cross-references we're pushing, they're all pushes. But this one is in the function crypto reading file. And we see if we look at these other 4, it's used inside the encrypt directory recursive as the argument. Same thing with here, just the param 4. And we'll skip to the last one. And again, same thing as the argument. So the only different one is going to be this one in the crypto reading key file. And just from the function name, that sounds like the right one anyways. So we select that. And so when we import a key, we are importing the key, and it's going to be imported into the last parameter. So we see we're importing into the file A's protection key. So we want to know what we're importing. So if we go to the MSDN to import key, the second parameter is the data that we're importing. So let's go back to graph view. So the second parameter is EDI. I select that and scroll up. And I see that's the buffer I'm reading in. So I need to know what file I'm reading in from. So I select the ESI, which has the handle, and scroll up. And I see it comes from create file. The first argument of create file is the file name. So I'll hit L to label and call this G for global and put file AES protection key file name. And then I select it, and I'm going to do Control-Shift-F to find the cross-references. Again, let me just go to the first one. And I see here I have 1, 2, 3, 4 references, and that looks like 1, 2, 3, 4, plus the one we just used. So this is all the places used. So I can see I'm copying this global variable into this file name, and then I'm concatenating or appending the string public onto it, and then I'm checking if that file exists. If it exists, I exit out. If it doesn't exist, I go to this crypto generate and write key file stuff. So that means the file name looks like it's this looks like a file path, and then the file name ends in the public. and it looks like we're probably going to create it in this function. So let's go ahead and label this first function or global variable, auto label, and call this file AES protection key file path. And just so we can see this is correct, we can tell from context that's what it is. Let's follow the cross references and go to the first one. And we see here we're getting the Windows directory. And then based on the OS, we are concatenating onto the end of that path the appropriate path based on if we're XP or not. So that tells us everything we need to know. It is the file path. So Alt left to get back. So we know our file name ends in public. So let's follow the cross-reference for public. Control Shift F. And for some reason here with this Unicode one, it finds every Unicode referencing here, which is not what I want to see. But since we can tell from context, we're checking if that file exists. If it doesn't exist, we come into this generate and write key file stuff. That means I know this file path is basically created in this function here just from context. So let's go ahead and go in here. And since this is a crypto function, instead of just looking for the public key file or that public file, we're just going to walk through here and kind of analyze this whole function, looking for all the crypto stuff. So I see I'm copying my protection key file path into this local 8 echo 0. So I'll hit auto label, and I'm just going to call this one the basically same as the file A is protection key file path, but I will take off the G because it's not global. In this case, it's just a stack variable. All right, so I see this user unique string. I'm checking if I'm XP or not, and then I'm acquiring my context is. I know acquired context is basically just background utility code. Not really concerned about that. And then I call this crypt generate key. So if you remember crypt generate key, 6610 was the AES256. Just to verify, we'll come back to this algorithm ID, and we see AES256 is the 6610. So let's go ahead and put a comment there, semicolon, AES256. And that key goes into the last parameter, which is the local 10, auto label. And this one, because we're going to call this file once, or this function once, instead of the file AES key, this one is really, I'm just going to call it generated AES key. Now I generate another key. To generate key, we look for that second argument is the algorithm ID. So in that case, this is EDI. So scroll up and see what EDI is set to. We're just looking for EDI to be highlighted. We see it zeroed out and then incremented. So EDI is 1. Alright, so if our EDI is 1, let's go back to our algorithm IDs. And if we scroll through here, look at these constants, you see these are all kind of large values. There's no kind of like 1 in there. They're all large numbers. So if I go to the generate key function, and I look in this algorithm ID, I see these algorithm IDs are basically for symmetric keys. And we also have this little part down here that in addition to generated symmetric keys, we can also generate a public-private key pairs or an RSA key pair. And you generate one of those, you have the algorithm ID to either key exchange or the signature. So if I go back to the flat view, I can look up my WinCrypt. I'll call this AT key exchange. And I don't see what the value is, so if I right click and do edit, you see it wants me to open it for edit. I hit yes, it won't let me open it up. So I'm not sure, short of maybe copying that to be able to see it, why I can't view that value. So I'm going to go back to the MSDN, and I basically from GitHub, I downloaded WinCrypt, and we look for the AT, and we'll have to do pound define AT, and we see here key exchange is the value 1, and that's the value we want. So I'm going to go back to my graph view, and I'll hit a semicolon, and I'll call this AT key exchange. So that means I'm basically making RSA a key pair out of here. So that's going to go into the last parameter, which is local Charlie, hit auto label, and call this generated RSA key pair. Because it's supposed to public and private key pair there. I'm going to export my generated RSA key pair. And now you notice here, we see EBXs, how we're passed the same parameter multiple times. If we scroll up, that's used over here. If we keep scrolling up, let's find that EBX value. We're expecting it to be null. And we see up here, we zero it out. So you can kind of tell how it's used as a null variable, because oftentimes we have the same register push multiple times. It's because you have a null variable. So remember when we mentioned we had the export key, and we call it down here, we call it again. That's because we're doing this, we're exporting the key. The size is going to be the last variable, which is local 14. Then we allocate space based on how big that size comes back to. And then we go through and using that size, we export it. And in this case, it's going to be what we just allocated, the EBX, is where we're exporting the key to. So we want to know what type of key we're exporting. Let's go back to MSDN. Look up the export key. And we want to know the blob type. And that's going to tell us what type of key we're exporting. And we can see we're doing either a private key or a public key because we know this is an RSA key pair. So if we go back to here, because it's the RSA key pair, and let me hit auto label because I missed the Y in that key. Alright, so this 6, I'm going to set ed equate, and I'm going to look up, I'll just check out public first. And in this case, we can see we're exporting the public key blob. So I'll double click that. And that means this EBX is up here, we're allocated. I'll go ahead and label that, hit auto label, and call this one the generated RSA public key exported, because I think this is the one we exported. And the public key you basically export without a protection, because it's just in the clear because it's a public key. And now we see we build a string, we copy this file AES protection key file path into local 494, and then we append the public key or public string onto there. We pass that into create file, and we go to the fifth argument, 1, 2, 3, 4, 5. It tells us how we're opening the file, set ed equate, and 2 is going to be create always. So we're creating a brand new file, basically with the public name, and then we write EBX out to that. So we select the EBX, scroll up, and we see EBX is our generated RSA public key, which was exported. So that means the file public is the generated RSA public key, and that's how we're protecting the file AES key for each file. Alright, so we write that out, and then we close the handle, and now we're going to export a key again. Again, we're doing the generated RSA key pair, and then we're protecting that with the generated AES key. But remember, when we call this export key, we call it first to get the size. Local 18 gets the generated size for the buffer. We allocate space into local 1 Charlie, and that's in EAX. Sorry, let me scroll up. Sorry, right here, EAX. And then we export that key into there. So this RSA key pair, we're exporting 7. So we hit ed equate. And if we already exported the public key, this one's likely to be the private key blob. And we're right about that. So that means this local 1 Charlie, I'll hit auto label and call this the generated RSA private key exported. And that's protected by the generated AES key, because the private key, obviously, you don't want to be in the clear like you do the public key. Now we're going to import a key. So when we import a key, we're going to look for the second parameter. So if we go back to MSDN, we see the import key. The second parameter is the data we're importing. All right, so we'll import this global variable. Let's go ahead, go back to the flat view and see what this looks like. So we're going to double click this. And we see here this RSA1. So you probably don't know what that is immediately, but with a little bit of Googling and checking the MSDN, we can see that this RSA public key, so this structure has this magic value, and it's set to RSA1 for public key or RSA2 for private key. So I know that I'm basically reading in a public key because I had the RSA1 in there. So if I pull up this base provider key blobs, I can see my public key blob. starts with the public key structure, followed by the RSA public key, that's what we just showed you, followed by the actual modulus of the key itself. So this public key structure has the basic type, and then version, reserved, and the algorithm ID. And we can see these types are these like key state blobs. And we can see public key blob is a type 6. So let's go back to Ghidra. And since we basically know what this is because of RSA1, I'm going to right click this global variable, do data, and then do choose data type. I'm going to call this the public key structure. I'll double click it. And then we apply that and we see if we expand this out, it has the type with the 6. And so if we go back and double check that, 6 was the public key. That's what we expected. We have the version, and then this algorithm ID is alpha400. If we go back to the algorithm ID, we can control F, and alpha400 we see is the RSA key exchange. So all that makes sense. So basically, at this import key, we're importing a RSA public key, which is hard-coded inside of here. It's going to be stored in this local 28. So I'm going to hit auto label and call this hard-coded RSA public key. Alright, so we have our export key. Remember, we call this usually twice in a row. Export the key, get the size, allocate space into EBX, and then we export the key. So we're going to export the AES key, protected by the hard-coded RSA public key. And this type 1 here, we can, let's see if we set ed equate. And this should be simple blob, because the symmetric keys generally do as a simple blob. That part's not super important. It's the fact that it's the AES key protected by the imported RSA public key is the important part. So this export is going to go into EBX. And we don't have any local variable named that. Now we see we're building a string on the same file path of unique ID do not remove. We're going to create a file. Let's see what file we're creating. The full local delta 2 Charlie. Let's scroll up. And we see this is unique ID do not remove. We go to the 5th argument, set ed equate. And this is the create always. So creating a brand new file called unique ID do not remove. And then we'll write into that file the generated RSA private key, which we exported. After that, we set our file pointer. We go to the 4th argument, ed equate, and we do, this is file n. We set our file pointer to the n, and we write EBX onto it. So let's scroll up and see what EBX is. And we see here, this is the, you see right up here, the virtual alloc, the exported generated AES key, protected by the hard-coded RSA public key. So we're almost done with this now. We basically build that unique ID do not remove file. We free up the store keys, free up some space. They have the acquire context to probably release it. And then we basically exit out. So now we basically analyze this whole function. Let's go up to the very top. Initially, when we named this the first pass through, I'm going to hit auto label. We called it a crypto generate and write key file stuff. That's pretty accurate. So I don't really need this stuff on there because now we know everything it does is the generates and writes key files out. They both the public and the unique ID do not remove. Go ahead, enter. We'll follow the cross references and go to where it's called because we also had a wrapper function here. And now we know this does the same thing. All it does is call that function. So auto label, and we'll take these stuff off of this name too. Again, as we find out more about the names, we iterate or create the names a little bit more accurately. And let's find this cross-reference, Control-Shift-F, and get back to where it was called. So that's the majority of the crypto. Let's kind of go to Notepad and Notepad++ and write out what we have. We can say we'll say for each file, we generate a new AES 256 key, encrypt file with AES key, and then we append Hermes plus stuff string, and then append, and we'll call this in fact create a new file AES key, an encrypt file with file AS key, append file AES key, protected with generated RSA public key. We have the public, in fact, this is all uppercase, public file contains generated RSA public key. And then we have the unique ID do not remove file contains, and this was the generated RSA private key protected with generated AES 256 key, and then was also followed by the generated AES 256 key protected with the hard-coded RSA public key. Now we have, let's talk about how to decrypt each file. So basically walking through everything we know about the crypto, and we're going to go through the steps of how you decrypt a file and build a decryption program to see if there's any flaws in the implementation program or protocol. Because of the fact that it's using WinCrypt and these Microsoft APIs, we know the key generation is going to be legit, and there probably won't be any flaws in that. So the only place we can find a flaw is in the methodology of how they implement the key exchange and basically get the encryption keys and the files back to the actor and the decryption program back to the victim. But if we don't understand how you build those processes, we won't know where to look for vulnerabilities. So to decrypt each file, we need to obtain unique ID do not remove file, and then we use actor RSA private key to decrypt generated AES 256 key, and use generated AES 256 key to decrypt generated RSA private key, and then use generated RSA private key to decrypt file AES key, and then decrypt file with file AES key. So that's how you decrypt each file. So the last thing we want to know about is how would we to build a decryption program. This is just so we can kind of talk through this a little bit. So basically, actor needs to obtain unique ID do not remove file, and we actually put file details. And then they need to decrypt decrypt generated AES 256 key, and then decrypt RSA. Actually, let me look at this. Decrypt generated RSA private key, and then hard code generated RSA private key into decryption program, and then implement file decryption steps starting at star. And we can see here, basically once we hardcode the generated RSA private key, we would be at this step here, use generated RSA private key to decrypt the file AS key. Go put the star there. And so that's basically how the decryption program would work. So again, we know that the key building methodology is legit because Microsoft built that. We know look at this, the key exchange protocol looks like they're using a proper protocol of using a public-private like asymmetric key pair to exchange, they're also using a generated RSA key pair that's generated for each host. So that means that each host is going to have different key pair, and so one decryption program won't work through multiple hosts. If instead of generating the RSA key pair per host, they would have encrypted the file AES key with the hard-coded public key of the actor, that would mean that every decryption program would have to have the actor's private key in there, and so the single decryption program will work for every host. The only way around that would be that if the actor created a new ransomware with a different RSA key pair for every victim they're going for, and if you're doing things like drive-by downloads or you're not doing targeted victims, then that obviously wouldn't make a lot of sense. So the fact that using the RSA key pair that's generated per victim, and then they're using that for the key exchange process, basically means they're implementing the key exchange in a proper way, and it doesn't look like there's any flaws here. So now we have a full understanding of the crypto methodology. We know each file is encrypted with a random AES-256 key. That key is protected with a generated RSA key pair. That key pair is properly protected with another with an RSA key pair and another generated AES key. And basically that means that there isn't really a vulnerability in this cryptography methodology. And we also know when we have each file that we have the Hermes string, and then follow that Hermes string, we have the AES key, protected with that RSA public key. So let's go back to Ghidra and see if there's anything else we want to talk about for the crypto, because that tells us all the general crypto stuff that we need to know. So if we want to write a report, we could write it. We can identify these files pretty easily through Yara if they're encrypted with something with like that Hermes string, so we know that's in there. All right, so let's look at this next function. We have this crypto reading key file. So now that we know something related to crypto, since this video is all about the crypto, let's go ahead and figure this out. Let's double click this. So we're acquiring our context. So again, that's kind of background noise utility functions don't really care about. We create a file. So we're going to do the fifth argument, this 3 set ed equate, and this is going to be open existing file. So we're opening the file for the AES protection key file name. We get the file size, allocate space, read in the file, and we read that file into EDI, and then that's what we import the key into the AES protection key, and then we exit out. So now we can tell this function, we can name this a little bit better now. Let's hit L to label. So instead of just crypto reading key file, let's call this crypto read in generated RSA public key file. Let me make sure that I read that the right one. Yeah, because we're reading in the AES protection key file name. And if we check back here, we have our files were file AES key was protected with the generated RSA public key. So got that correct. So I'm going to hit Alt left to get back. So that basically updated that name. So now we have a little bit more context. So we can see we generate and write key files, and then we read in the generated RSA public key. The only reason really to do that, because this would already be potentially memory from this generate, is that this allows you to have persistence. It allows you, if your program gets stopped, to basically start up because you can read in the files. Because once you generate these key pairs, you can't stop the ransomware program and start up where you left off without and still use those same key pairs unless you have a way to read them in. So it's just a way that they generate them, write them onto disk, and then they read it in. So that way, again, they can basically use it for persistence. If the program gets stopped, they can restart up, and you'll have the same key pair. Because remember, if we go back to our decryption program, we have to hard code the generated RSA private key into the decryption program. So if we come back here and we generate this key file more than once, and we have 2 different RSA generated RSA private keys, then we can't write a single decryption program for this victim. So this way allows us to basically have a more robust ransomware methodology. We decrypt our data sections, and this one's not clear. We have read and parse file stuff, but this is actually one of the last crypto functions. So we're going to go ahead and analyze that now because I know it's a crypto, and so we'll get this since this whole video is dedicated to crypto. So we decrypt some configuration data here. So we see simple XOR crypto loops. we build a string. So not worry about what string we're building. We're doing multiple string cats. We copy this AES protection key file path into EAX. And then we append on unique ID do not remove. Remember that it has our generated RSA private key followed by the generated AES key. We open that existing file. We get the file size. It looks like we convert some integer to an ASCII. Probably the file size because we see it's from ESI. Yep, would be the file size. And then we read in that file. It's going to go into this buffer local 640. And now looks like we're checking some buffer. We're looking for the greater than sign, greater than sign, greater than sign, and another greater than sign. If you look at this buffer is a buffer plus ECX, another buffer plus ECX, another buffer ECX. Just like the last time we saw this, notice this buffer value or this global variable value 4088 delta 0, 4088 delta 1, 4088 delta 2, 4088 delta 3, and so forth. So we're basically incrementing the start of this buffer by 1. Instead of incrementing ECX, we're incrementing our buffer value here. So if we find those 4 greater than signs in a row, then we're going to convert this I to A. So we're going to convert, looks like this buffer here. This is EBP. Again, Ghidra made this error again, where they couldn't designate this as a stack variable. This is just a 2's complement for a negative number, plus what looks like a increment, what looks like a loop counter. So we grab this integer value, convert it to an ASCII, so I to A is going to come out into local 8. We grab that byte out, and we move it into this delta 4, and then the byte plus 1 right here into the delta 5. So if we look at these values here, so we see this last greater than sign ends at delta 3. We increment 1 more to delta 4, and that's where we append that to, and then delta 5, and then we increment that by 2, and I guess it's a delta 6. So basically we're reading in this buffer, and then we're appending that onto this global variable. So let's see what this buffer is, the FFF9 Charlie 4. I just scroll over until we see it highlighted, and we see it's where we read in the file. So that FFFFF9 Charlie 4 is local 640. Let's scroll back over. We're going to right click. And again, don't know why this is coming up this way where the add references is not showing up in this menu. Literally, the other times I've done this, it shows up. So something, again, just Ghidra, the graph view is a little bit buggy. Let's go back to the flat view. And we can select this. It's actually, so we see it's not visible here. So let's just go back to the graph view. So I could go into this flat view, expand my columns and see it bigger. I don't want to change that right now. So because I know the shortcut key is the R, let's hit the R, hit the plus sign, do the stack, and then minus 0x, and I think it was 640. We'll double check it. So the 640, yep, is indeed our buffer. So in this case, we write in our file, this unique ID do not remove. We write it into this buffer 640, and then we loop through the buffer, and we read in each byte of that key file. Remember that unique ID has the 2 generated private keys, the AES and the RSA private key. We convert that from an integer into an ASCII string, and then we append that onto this global variable. So you may be wondering, okay, what that global variable is used for. And if you know a little bit how ransomware works, there's really only one real main possibility. Is when remember, let's go back to our notepad. So in order to build the decryption program, you need to obtain that unique ID do not remove file details. So the 2 different ways you can obtain that is you can tell the victim to send the file with the Bitcoin, or you can put the details out and then tell them to send the details. So basically you need the file content. So oftentimes what actors will do is they'll either reference a file in the ransom note, or they'll put the actual details in the ransom note, and then they'll tell the victim to send it to the malicious actors. So in this case, this looks like this file is probably building the ransom note. And so let's check the beginning of this buffer. So remember, this is all, all starting with this delta 0 buffer. So let's follow these cross-references. Control-Shift-F. So we see it's in this decrypt data section. It's also drop and open ransom note stuff, and then the read and parse file note. So the fact that that's used in the drop and open ransom note, and then drop ransom note, is another indication that's probably the ransom. But it's also in this decrypt data section. So let's follow that cross-reference. This will be the easiest place to see if it is indeed the ransom note. So it's a 4088 delta 0. And let's find this function, Control-Shift-F, and go to the cross-references. So we're basically just going to run this and look in the debugger and see if it looks like the ransom note to kind of confirm our suspicions based on context and kind of private or previous knowledge of how ransomware works. So you can see here when you do the deep dive analysis methodology, the more understanding you have of the programming algorithms, the more context you have and the easier it is to make these decisions and educated guesses, as opposed to just having kind of like unknown global variables. You can tell from context and from the general programming algorithms, since you know it's ransomware, of what you're likely doing. So let's open up this file inside x64 32 debugger. We're going to F9, get it in the space, the user space. And then we'll go back to that graph view. So we want to go to address 4411. So Control G, 404411. And this is the function we want to do. So I'm just going to select it, right click. I'm going to look for the set new origin here. I'm just going to change the EIP right to it. I'm going to F7 to step into it. And then the address I want, I'm going to hit the hex view, hex dump, hit Control G. And I believe it was 4088 delta 0. So now I'm going to step through this function. I see here, you see it's starting to decrypt here. So that means I'm in the decryption loop. I'm just going to go past it. So watch this hex dump at the bottom here. I'll hit F4, and we see we decrypted that data block. So let's scroll through here. I see the Hermes Ransomware title. And I'm just going to scroll through here until I see something that tells me if it's the ransomware node or not. And this is all looking like the HTML header stuff. I'm still in the header. And just scrolling through this. So I see a bunch of nulls here. And before the nulls, I see 1, 2, 3, 4 greater than signs. Let me scroll up a little bit. And now you see, let's see if you can see here, all your important files are encrypted. So it does look like the ransom note. I see 4 greater than signs, followed by a bunch of zeros. So that's probably where I'm going to be writing my that unique ID do not remove encryption key values. So they basically put a placeholder with nulls there, and I'll be overriding them with the values I need. So just the fact that we have the HTML file title with your Hermes Ransomware, and then we see the string all your important files are encrypted, that tells us it's a ransom note. So I'm going to update this read and parse file stuff to L for label. I'm going to call this build ransom note, including crypto, and we'll call it including generated crypto keys. That's really what it's doing. So now we updated our names a little bit with the crypto stuff. So we can see scrolling through here, we had this delete file or copy start stuff. We'll figure that out in the next video. And we generate and write the key file wrapper. And then we're going to read in that keys we just generated. We're going to decrypt the data section. We're going to build the ransom note, including the generated crypto keys. And then we go through the get logical drives and start the encryption process. So that's really everything we need to talk about the crypto today. So hopefully that gives you a good idea of how the Microsoft WinCrypt APIs work. You can get an idea of how the general methodology of how ransomware works. So you can see here, we know how each file is encrypted. We know what the public file contains. We know what the unique ID do not remove file contains. We know the general steps of how to decrypt a file. And then we know the general steps of how to build a decryption program. So we really should have a better understanding of how ransomware crypto works. And so that if we look at other ransomware programs, it should be a lot easier to understand and identify and label the crypto algorithms, as well as look for the key indicators to see if there's any vulnerabilities in the implementation method. So that's everything we need to talk about today. And the next video might be the last video. We either have one or two more, depending on the next video goes. We're going to finish up finding the IOCs and labeling the functions. So we're going to use a little bit more of the debugger to identify the last couple of functions we don't have good names for. And then maybe we'll look for the final IOCs if we have time, of things like exactly which folders are targeted and ignored, which extensions, things of this nature. So, and again, just to kind of as a reminder, if you want to look at this marked up Ghidra file, I'll put this up in my GitHub page once we're done with the video series. And so, just look at that. It'll be linked in the video description. And if you want to download this ransomware to practice on your own, the hash is listed in the video description, and you can download it from Malware. So I hope you enjoyed the topic today. If you did, please like the video and subscribe to my channel to get notified when new videos come out. I also love to know what you think, so leave me comments below. If you want more reverse engineering tips, follow me on Twitter. If you're interested in structured stringing, check out my website for the malware analysis class that I offer. And until next time, keep on practicing and try to learn something new every day.